Welcome to this discussion on LeetCode problem number 465, Optimal Account Balancing. In this problem, we will explore how to minimize transactions to settle debts among individuals efficiently. We'll break down the problem, analyze different approaches, and understand how to apply key concepts to solve it effectively. Let's get started. The problem we're solving is called optimal account balancing. Imagine you have a list of transactions, where each transaction is represented as, from _I to _I, amount _I. Here, from _I is the person giving the money, to _I is the person receiving it, and amount _I is the amount being transferred. Your task is to determine the minimum number of transactions required to settle all debts between the people involved. For input, you'll receive a list of these transactions, where each is structured as, from _I to _I, amount _I. The output will be a single integer representing the smallest number of transactions needed to settle all the debts. Let's explore an example to understand this better. In the first example, the input is transactions equals 0, 1, 10, 2, 0, 5. The output is 1. Let's break this down. Person 0 owes $10 to person 1, and person 2 owes $5 to person 0. Instead of handling these debts in multiple steps, we can settle everything with a single transaction. Person 2 transfers $5 directly to person 1. This clears all debts in just one transaction. Now, consider a slightly more complex example. In the second example, the input is transactions equals 0, 1, 10, 1, 0, 1, 1, 2, 5, 2, 0, 5. The output here is 2. To understand why, we first calculate the net balances for each person. Person 0 has a net balance of plus 4, person 1 has a net balance of minus 4, and person 2's balance is 0. This means person 1 owes $4 to person 0, while person 2 has no outstanding debts. These balances can be resolved in two transactions. First, person 1 transfers $4 to person 0, and with that, all debts are cleared. Finally, let's examine an edge case where there are no transactions. In the third example, the input is an empty list of transactions, transactions equals. The output is 0, because with no transactions, there's no debt to settle. This highlights the simplest case where no action is needed. Now, let's look at the constraints and edge cases to keep in mind. The number of transactions can range from 1 to 8, and each transaction is always well-formed, meaning from _I and to _I are valid person IDs, and the transferred amount is positive. Edge cases include situations like circular debts, where the amounts cancel out, or when all balances are already 0. In every scenario, the goal remains the same: minimize the number of transactions required to settle all debts. When tackling problem number 465, optimal account balancing, the primary objective is to minimize the number of transactions needed to settle debts among individuals. One initial approach to consider is the brute force method, which uses naive backtracking. The intuition here is straightforward: for each person with a non-zero balance, we attempt to settle their debt with every other person who also has a non-zero balance. This involves recursively exploring every possible way to settle these debts and keeping track of the minimum number of transactions required. A few key observations help guide this process. First, each person will either owe money, represented by a negative balance, or be owed money, represented by a positive balance. This means the problem boils down to minimizing the number of transactions needed to clear these balances. To implement this, we calculate each person's net balance, use backtracking to explore transaction combinations, and track the minimum transactions during recursion. However, this approach is computationally expensive, with a time complexity of O(n), due to the factorial growth of possibilities. While it's simple to understand and implement, this brute force method becomes impractical for larger datasets because of its inefficiency. To improve on the brute force approach, we turn to optimized backtracking with pruning. By introducing pruning techniques, we can significantly reduce unnecessary computations and improve performance. The intuition builds on the brute force method but incorporates strategies to skip over redundant paths. For example, if two individuals' balances cancel each other out, their debts can be resolved in a single transaction. Additionally, sorting balances or avoiding redundant transactions helps narrow the search space further. The algorithm begins by calculating the net balances for all individuals and filtering out those with a zero balance, as they don't require any transactions. Backtracking is then applied to explore transaction combinations, but with pruning logic to avoid paths that exceed the minimum transactions we've already found. By pruning branches where the remaining debt is worse than the current solution, we avoid unnecessary computations. This reduces the search space, making the approach feasible for moderate-sized datasets. While this method is still exponential in the worst case, it's significantly faster than naive backtracking. The trade-off here is that while it's more efficient, performance may still degrade for very large datasets, though it achieves a good balance between simplicity and practicality. Another way to approach this problem is through a graph-based solution, which models the debt balancing problem as a directed graph. Here, nodes represent individuals, and edges represent transactions. The goal is to minimize the number of edges in the graph, which corresponds to minimizing the number of transactions required. This perspective aligns with concepts from flow problems in graph theory. To implement this, we first build a graph from the transaction data, where edges represent the flow of money. Algorithms such as minimum cost flow or cycle cancellation can then be applied to balance the graph. The number of edges in the resulting balanced graph gives the minimum number of transactions. While this approach is conceptually appealing and provides a strong theoretical foundation, it comes with some challenges. Graph-based methods often involve more complex implementations, and their time complexity can reach n squared, or higher, depending on the specific algorithm used. While this makes the approach less practical for this specific problem, it's worth noting that it offers an alternative framework for thinking about the solution. However, the complexity of implementation and analysis often outweighs the benefits for this particular use case. After evaluating the different approaches, the chosen strategy for this problem is the optimized backtracking with pruning method. This approach strikes the best balance between simplicity, efficiency, and practicality. While graph-based solutions offer a theoretical alternative, they're more complex to implement and don't provide a significant performance advantage for this specific problem. On the other hand, the naive backtracking approach, while easy to implement, becomes computationally prohibitive as the input size grows. There were a few key insights, or aha moments, that informed the decision to use optimized backtracking. First, the problem can be reduced to balancing net debts rather than focusing on individual transactions. Second, pruning the search space, such as by skipping redundant transactions, dramatically improves efficiency without compromising correctness. Lastly, pre-processing the data to reduce the number of non-zero balances simplifies the problem even further. By comparing the trade-offs, it's clear that optimized backtracking is the most practical and efficient choice for solving real-world instances of the problem. This approach ensures a robust solution while keeping implementation complexity manageable. This problem, optimal account balancing, challenges us to minimize the number of transactions required to settle debts within a group of people. Each transaction specifies that one person pays another a certain amount. For instance, if the transactions are 0, 1, 10, 2, 0, 5, it means that person 0 paid person 1 a total of 10, and person 2 paid person 0 an amount of 5. Our aim is to reduce the total number of transactions while ensuring that every individual's net balance is brought to 0. The first step to solving this is to calculate the net balance for each person. We use a dictionary where the keys represent individuals, and the values indicate how much each person owes or is owed. A positive balance means the person is owed money, while a negative balance means the person owes money. This sets the foundation for determining who needs to settle debts and by how much. To compute the net balance of each person, we iterate through all the transactions. For each transaction, we update the balances of the payer and the payee. For example, using the transactions 0, 1, 10, 2, 0, 5, we calculate the balances as follows: person 0 has a balance of -5, person 1 has a balance of 10, and person 2 has a balance of -5. This means person 0 owes 5, person 1 is owed 10, and person 2 owes 5. Next, we filter out individuals with 0 balances since they are already settled and do not need further transactions. We extract all non-zero balances into a list called debt. For the balances computed earlier, this results in the list debt equals -5, 10, -5. These are the values we will work with to minimize the number of transactions required to settle all debts completely. The next step involves using a backtracking approach to explore different ways of settling these debts. The backtracking approach helps us find the minimum number of transactions required to settle all debts. The idea is to recursively match a person with debt to another person with credit until all balances are settled. At each step, we skip over any individuals who already have a balance of 0, as they no longer need to participate in the settlement. For each unsettled person, we look for another individual with an opposite sign in the debt list, meaning one owes and the other is owed. When a match is found, we temporarily settle their debts by adjusting their balances and then recursively attempt to settle the remaining debts. After exploring this path, we backtrack by restoring the original balances, allowing us to try other potential matches. For example, if person 1 has a credit of 10 and person 0 has a debt of -5, we can settle part of their amounts and move forward. This recursive process continues until all debts are resolved, and we track the minimum number of transactions encountered across all possible paths. To begin the backtracking process, we call the function settle debt 0, where debt is the list of non-zero balances and 0 is the starting index. The base case for the recursion occurs when all debts are settled, which is when every value in the debt list is 0. At that point, we return 0, indicating that no further transactions are needed. In the recursive case, we attempt to settle the debt of the current person with another individual who has the opposite balance, meaning one owes money and the other is owed money. By minimizing the number of transactions at each step, we gradually work toward the optimal solution. Skipping over settled debts ensures we don't perform unnecessary computations, while the backtracking mechanism allows us to explore multiple ways of settling debts and prune suboptimal paths. This combination of recursion, backtracking, and greedy choices ensures that we find the smallest number of transactions needed to fully settle the debts. The algorithm relies on a few key data structures to achieve its goal efficiently. First, a dictionary is used to compute and track the net balances of each individual, allowing quick updates as we process each transaction. Next, a list called debt is created to store only the non-zero balances, significantly reducing the problem size by focusing only on unsettled individuals. Finally, the recursive call stack is used during backtracking to explore all possible ways of settling debts. This approach, while powerful, has a worst-case time complexity of O(n), where n is the number of unsettled debts, because we may need to explore all permutations of debt settlements. The space complexity is O(n), stemming from the recursive stack size. While the algorithm is computationally expensive in the worst case, it is effective for scenarios with a manageable number of unsettled debts, ensuring an optimal solution by systematically minimizing transactions through backtracking. To solve the problem of optimal account balancing, we start by calculating the net balances for each person based on the given transactions. Here, we use a default tick to store these balances. For each transaction, the amount is subtracted from the payer's balance and added to the payee's balance. Once we have all the balances, we filter out those that are 0, as they represent individuals whose accounts are already settled. This gives us a list of debts, which contains only the non-zero balances. Next, we define a backtracking function, DFS, to minimize the number of transactions required to settle these debts. The function starts by skipping settled debts, and if all debts are settled, it simply returns 0 as no further transactions are needed. At this point, we initialize min_transactions to infinity to track the minimum number of transactions as we explore different possibilities. Now, the function attempts to settle the current debt at the given index with subsequent debts in the list. For each subsequent debt, we check if it has the opposite sign to the current one, as this indicates a potential settlement opportunity. If so, we adjust the subsequent debt by adding the current debt to it, effectively simulating a transaction that settles part of the debt. We then recursively call the DFS function for the next index, and update min_transactions to reflect the minimum transactions required. After this recursive step, we backtrack by undoing the adjustment to ensure the original state of debts is preserved for other possibilities. Once all options have been explored, the function returns the minimum number of transactions needed to settle all debts. Finally, the min_transfers method returns the result of calling DFS starting from the first index. To start solving the problem of optimal account balancing, we first need to calculate the net balance for each person involved in the transactions. Here, we use a hash map called balance map where the key is the person's ID and the value represents their net balance. For each transaction, we subtract the amount from the from person's balance and add it to the to person's balance. Once we've processed all the transactions, the map gives us the net balance for each person. Now, since we're only interested in unsettled balances, we extract values from the map into a list called debts, filtering out any zeros. This gives us a streamlined view of the people who owe money or are owed money. Finally, we define a recursive backtracking function, DFS, which will help us minimize the number of transfers required to settle these debts. Let's dive into how this function works. The DFS function begins by skipping over any debts that are already settled. If we've gone through the entire list and all debts are clear, we return 0 as no more transactions are needed. Otherwise, we set up a variable min transactions to keep track of the minimum number of transfers required. The key part of the algorithm is attempting to settle the current debt at index with subsequent debts in the list. If two debts have opposite signs, it means we can potentially settle one with the other. We adjust the debt at the current position and make a recursive call to handle the rest of the list. After that, we backtrack by resetting the debt to its original value to explore other possibilities. This ensures we consider all possible ways to minimize the number of transactions. In the end, the function returns the smallest number of transfers required to settle all debts. To solve this problem, we start by calculating the net balance for each person based on the transactions. For the input transactions equals 0, 1, 10, 2, 0, 5, we initialize an empty dictionary called balance. After processing the first transaction, 0, 1, 10, person 0 owes $10, and person 1 is owed $10, so the balance becomes 0 minus 10, 110. Next, we process the transaction, 2, 0, 5, where person 2 owes $5 to person 0. Adjusting the balances, we get 0 minus 5, 110, 2 minus 5. Finally, we filter out anyone with a 0 balance, leaving us with the debts array, -5, 10, minus 5. The next step is to minimize the number of transactions needed to settle these debts using a recursive backtracking approach. Starting with the first debt of -5 at index 0, we attempt to settle it with the creditors. First, we try settling with the debt at index 1, which is 10. Updating the debts array to reflect this partial settlement gives us -5, 5, minus 5, and we proceed to the next step by recursing into the next index. With the updated debts array, -5, 5, minus 5, we look at index 1, where the debt is now 5. We skip this index temporarily since it reflects a positive balance, and instead, we try settling the remaining debt at index 2, which is -5. Settling these amounts fully cancels out the debt at index 2, leaving us with the updated debts array, -5, 5, 0. At this point, we recurse further, and since all remaining debts are resolved, the recursion returns 0, indicating no additional transactions are needed for the current path. We backtrack to explore other possible settlement paths, but ultimately, the minimum number of transactions required to settle all debts in this case is determined to be 1. For the output, we return 1. Next, we consider a slightly more complex example, starting with the input transactions equals 0, 1, 10, 1, 2, 5, 2, 0, 5. After processing all transactions, the balance dictionary becomes 0, 0, 1, 5, 2, minus 5. This means person 0 has no net debt, person 1 is owed $5, and person 2 owes $5. We then filter out any 0 balances, leaving us with the debts array, 5, minus 5. The goal is to minimize the number of transactions required to settle these debts. Starting with the debt of 5 at index 0, we attempt to settle it with the debt at index 1, which is -5. Fully settling these amounts results in an updated debts array of 0, 0. At this point, all debts are resolved, and the recursion returns 0, indicating no further transactions are needed. Since we were able to settle all debts in just one transaction, the minimum number of transactions required for this example is 1, and we return 1 as the output. Finally, we consider a scenario where all debts are already balanced. In the input transactions equals 0, 1, 10, 1, 0, 10, person 0 initially owes $10 to person 1, but the second transaction cancels this out by having person 1 repay $10 to person 0. After processing both transactions, the balance dictionary becomes 0, 0, 1 o'clock. Filtering out zero balances leaves us with an empty debts array, which means there are no outstanding debts to settle. As a result, the recursion immediately recognizes that all debts are resolved and returns 0. Since no transactions are required, the output for this example is 0. This highlights that when all debts are already balanced, no additional steps are needed to achieve optimal account balancing. The time complexity of solving the optimal account balancing problem is influenced by two main components: pre-processing the data and the backtracking algorithm. In the pre-processing phase, we first calculate the net balances for each person by iterating through all the transactions. Since each transaction updates the balance of two people, and there are t transactions in total, this step takes t time. After calculating the balances, we filter out those with zero balances to create the debts list. If there are p people involved, this filtering step takes p time. Together, these pre-processing steps lay the foundation for the backtracking phase that follows. In the backtracking phase, the DFS function explores all potential ways to settle the debts. The length of the debts list is determined by the number of people with non-zero balances, which is denoted as n. For each step, the function attempts to pair the current debt with the remaining ones. In the worst case, the first debt could be paired with n1 options, the second with n2, and so on, leading to a branching factor that results in at most n. Recursive calls. Each of these calls might involve iterating over the remaining debts, which takes up to n time. As a result, the backtracking phase has a time complexity of n*n. Combining this with the pre-processing phase, which contributes t plus p, the overall time complexity is dominated by n*n, since n is typically much smaller than p. When evaluating space complexity, we consider both the pre-processing and backtracking phases. During pre-processing, the balance dictionary requires space proportional to the number of people, or OP. Additionally, the debts list, which stores only the non-zero balances, uses n space. In the backtracking phase, the recursive DFS function utilizes the call stack, and in the worst case, the recursion depth can reach up to n, the number of people with non-zero debts. This means the call stack uses n space. Since the debts list is modified in place, no extra space is required for it. Combining these, the overall space complexity is p, as the pre-processing phase dominates and n is always less than or equal to p. Comparing the current solution to a brute force approach highlights the efficiency of the optimized method. A naive solution would generate all permutations of the debts and calculate the number of transactions needed for each permutation. This brute force method has a time complexity of n, as it involves generating n permutations for n non-zero debts and evaluating each one. The optimized approach, on the other hand, leverages backtracking with pruning. By attempting to settle debts incrementally and skipping already settled debts, it avoids exploring unnecessary branches. While the worst-case time complexity of n*n remains higher than the brute force's theoretical n, in practice, the pruning significantly reduces the number of branches explored, making the current solution much more efficient. Analyzing the best, average, and worst cases of this algorithm provides a clearer understanding of its performance. In the best case, if all debts are already settled, meaning the debts list is empty, the algorithm skips the backtracking phase entirely, completing in t plus p. For the average case, the performance depends on the distribution of debts and how quickly the algorithm can prune unnecessary recursive calls. This results in fewer recursive calls than the worst case, but still depends heavily on the number of non-zero debts, n. In the worst case, each person's debt must be paired with every other person's debt, leading to n*n recursive calls. This behavior is explained by the mathematical derivation of the time complexity. The backtracking explores all possible combinations, resulting in n permutations, with each recursive call contributing an additional n factor. Meanwhile, the space complexity remains p, dominated by the pre-processing and recursion stack requirements. When tackling this problem, there are several common mistakes to avoid. First, failing to reduce the debt array is a frequent error. Instead of focusing on the net balances of each individual, some try to simulate every transaction between all pairs, which greatly increases complexity and redundancy. Always simplify the problem by calculating a single net balance for each person. Another common pitfall is brute forcing all permutations of transactions. This approach results in exponential time complexity, specifically O(n), and is impractical for larger inputs. Instead, you should use backtracking with pruning to eliminate unnecessary paths and make the algorithm more efficient. Additionally, including individuals with zero net balance in the backtracking process is another mistake. These people do not impact the solution and only expand the search space unnecessarily. Lastly, an incorrect base case in the recursive backtracking process can lead to incomplete or incorrect results. Your base case must ensure that recursion stops only when all balances are settled, which occurs when all balances are zero. Addressing these issues is fundamental to building a correct and efficient solution. Handling large inputs inefficiently is another major challenge. For example, with up to 10,000 transactions, an inefficient algorithm is likely to time out. To address this, optimize your recursion and use memoization to improve scalability. Now, let's focus on some key insights for interviews. A critical strategy is to reduce the problem to net balances. Instead of tracking each transaction individually, calculate the net credit or debit for each person. This simplifies the problem significantly. Additionally, leverage backtracking with pruning to minimize the number of transactions. By skipping unnecessary paths, you can focus only on meaningful progress. Recognizing patterns is also essential. For example, you might decide between settling debts incrementally or resolving everything in one step. Understanding these patterns informs how you structure your recursion. Lastly, be prepared to discuss why your solution is optimal. Interviewers often expect you to explain time complexity, such as comparing the inefficiency of O(n) brute force to the more manageable O(2) to the power of n, achieved through pruning. This problem connects to several related challenges on LeetCode, which can help deepen your understanding. For instance, in LeetCode 1244, Design a Leaderboard, the focus is on efficient aggregation and optimization, much like reducing net balances here. Similarly, LeetCode 128, Longest Consecutive Sequence, emphasizes grouping and reducing problems to their core elements, an approach that's useful for breaking down this problem. LeetCode 140, Word Break 2, involves backtracking with memoization, which is central to finding optimal solutions efficiently. Lastly, LeetCode 282, Expression Add Operators, shares the concept of recursively exploring options while pruning paths that don't lead to valid results. Studying these related problems can strengthen your grasp of the techniques required for optimal account balancing and other complex algorithmic challenges. There are also alternative approaches to solving this problem, each with its own trade-offs. A greedy approach, for instance, aims to settle debts in the largest chunks first, which can quickly reduce the number of transactions. While this method is faster for approximate solutions, it may not always produce the minimal number of transactions. Another option is dynamic programming with state compression. By using bit masks to represent subsets of debts, you can solve the problem with more efficiency for large inputs. However, this approach requires significantly more memory and is more complex to implement. Lastly, a graph-based approach models debts as a directed graph, where you can use cycle detection to minimize transactions. This method is intuitive and visually represents the problem well, but optimizing it for edge cases can be challenging. Each of these approaches offers unique insights and is worth exploring based on the constraints and requirements of the problem at hand. Thank you for joining me in this walkthrough of optimal account balancing. We covered the problem, analyzed the backtracking approach, and discussed its complexities. Remember, practice is key to mastering these techniques. Don't forget to like, share, and subscribe for more content like this. See you in the next session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!